Hi, I'm Crispy. Welcome back to Making the mangoPi, the series where I take you through my PCB design process and show you the inner workings of the mangoPi. Today we're going to take a look at the SRAM interface, the Ethernet interface, the PCIe interface, and finally the FPGA I/O pins. Let's get started. First, let's update the SRAM schematic. The CE in CE pins stands for chip enable. All CE pins must be properly pulled high or low to assert them. When they are all asserted, the SRAM is enabled and you can read or write to it. The revision 2 schematic asserted the CE pins by default, but we want them to be deasserted by default. Next, since we know we want a 9 megabit SRAM, we can remove all the extra 0 ohm resistors and connect the address 15 net to the final address pin. 0 ohm resistors are useful in PCB design because if you want to connect a pin or leave a pin unconnected, you can simply add or remove the 0 ohm resistor on the final board. Now let's copy some data nets and address nets and connect them to some FPGA I/O pins. As I mentioned in the previous video, a lot of these connections will be changed once I know how all the traces are routed out of the FPGA. I am adding a fan tachometer pin and a fan PWM pin. This will allow the FPGA to control a 4-pin fan. I am also adding a few I/O pins for the PCIe interface. Now we can add the rest of the SRAM pins to I/O bank 15 of the FPGA. Most of the schematic will be the same, with the exception of changing the Ethernet jack, removing a redundant power IC, and removing extra resistors. I also need to change the Ethernet PHY's I/O voltage to be 1.8 volts so that it matches I/O bank 34's I/O voltage. With all that changed, we can now connect the Ethernet pins to the FPGA I/O bank 34 pins. Another important fix is that the ETH_RXCK pin needs to be connected to a clock-capable pin on the FPGA. With all that done, let's move on to the 4X PCIe interface. Much of the connections will be similar to the Compute Module's 1X PCIe connector, with the exception of having an additional 3 lanes. A lane is a differential pair used for sending or receiving data. If its name has a TX in it, then it sends data. If it has an RX in it, then it receives data. We will also connect the FPGA's JTAG pins to the JTAG pins of the PCIe edge. This will hopefully allow a computer to configure the FPGA. Per PCIe standard, the receiving differential pairs also need to have AC decoupling capacitors in series with them. I honestly don't know what these are used for, so if you do, then please let me know in the comments down below. Now we need to connect the transceiver pins to the FPGA. This gets a little bit weird. We connect the nets labeled as receiving RX to the FPGA GTP transmitters, and we connect the nets labeled as transmitting TX to the FPGA GTP receivers. This is because the TX and RX naming convention is in line with the thing controlling the PCIe interface, which for the FPGA's PCIe connection would be the compute module or your PC. So the compute module's transmitting lane is really the FPGA's receiving lane, while the compute module's receiving lane is really the FPGA's transmitting lane. We also have to reverse the order of the lanes, so the FPGA's lane 0 goes to the compute module's lane 3. FPGA lane 1 will go to the compute module lane 2, and so on. Let's also add a few user input buttons to the FPGA. Bank 15 has 8 analog inputs. Pins capable of reading analog voltages will have an AD number P or AD number N in their name. Analog inputs work in pairs. For instance, if you wanted to use the 0th analog to digital converter, then you would connect the AD0P pin to the side with higher voltage, and connect the AD0N pin to the side with lower voltage. At this point, I realized something was off. I had originally counted 56 I/O pins for the SRAM, but that was not adding up. Turns out, the SRAM really had 67 I/O pins. Luckily, this FPGA has a ton of available I/O pins, so we can make it work. The mangoPi will have 16 LEDs the FPGA can turn on and off. Since the pins controlling the LEDs operate at 1.8 volts and the voltage drop range for the LEDs is 1.7 volts to 2.2 volts, we don't even need to connect a current limiting resistors in series with them. And that completes the GPIO for the FPGA. Now there are a few small things I'll need to do that I'll do off camera, but that's pretty much the entire schematic. So the next step after this is to make the PCB. In the next video, we're going to convert the schematic to a PCB and start laying out the components on the board, and maybe even get some traces done. Thank you so much for watching. I hope you enjoyed the video. I'll see you in the next one.